Okay. So basically, today we have Chaka Mofoekeng, if I
Yep,
am not
Mofoekeng.
yes,
Mofoekeng, that's right.
from SAAO. Currently, he's working at SAAO with the Christian, I think, and he has very nice experience with software development. So he has been working on a lot of machine learning techniques using in radio astronomy. Okay, so I will just mute everyone because I can hear noise. Okay. So he has been part of University of Western Cape and University of KwaZulu-Natal for his master and bachelor's. So today he will be sharing his experience with the machine learning techniques he used in radio astronomy. So I will not take much time. I will invite Chaka to go ahead with his presentation. Thanks a lot. Please, can you share your screen? Okay, just a minute. Can you unmute, Chaka? You are muted, I think.
Sorry, Sunil, can you hear me now?
Yes, yes.
Okay, great. Sorry about that. Let me share my screen now. Everything is fine. Can you see my screen?
Yes, perfect.
Great. So good morning, everyone. Thank you for making time to today's colloquium. And today I'll be telling you about the work I've been doing for MSc. And so the topic of this project is deep learning for morphological classification of radio sources. But really the topic maybe could have been something like a robust and automatic source characterization pipeline that is based on deep learning algorithm. So for this project, I've been working with Mattia Vakari and Russ Taylor. So what motivated this project is the fact that we know science is undergoing data explosion and astronomy is leading the way on that. So to give a feel of this, on this slide, I'm displaying data rates that's bytes per night on the y-axis and of a particular telescope in a particular year. And please note that these figures are not true values. They're just an estimate to give you a feel of this. And this is from a paper by Kramer et al. 2017. So as you can see, in recent years, we've entered terabytes scale. So telescopes were estimated to produce over 10 terabyte, about 30 terabytes of data per night, the LSST, and we have TMT here. Probably the meerkat will be something like here, because recently I came across a paper by Priya and Anascape from Manchester, UK. So this paper was talking about how meerkat data is transported from CHPC last that, and ideally to UK's Iris. And here they gave a rough estimate of meerkat's data rate to be about 4 terabytes per second. So that's like roughly over 300 petabytes of data per day. So as you can see, that this gives you a glimpse of the data management and processing challenges faced in astronomy today. So here I'm showing you an example of data from Meerkat. I think this is Meerkat's first light image. It was released around July 2016, if I'm not mistaken. And usually for astronomers to process data from, say, Meerkat, they would usually take this image here. As you can see, there's these bright blobs which represent the radio sources, and astronomers would usually zoom in around this image to see the different sources and try to characterize them. So they would go on this image, get the source position at the center, and then try and get their counterparts. So this process already is taking a lot of time, and it's not sufficient to deal with the data flow or data rates expected, or data rates we're currently dealing with from the current generation of radio telescopes. So that's the motivation for this project. I mean, we need efficient and robust automated algorithms to deal with data processing in near real time. So yeah, that's what we set out to do in this project. So, and one can talk about automating some tasks without mentioning machine learning, and that's what we went for in this project. And because we were basically focusing on processing image data, we then worked with deep learning or convolutional neural networks, or known as convolutional neural networks. So here I'm showing you a basic layout of a convolutional neural networks. Usually they can be summed up by 3 layers. One, which is convolutional layer, which is usually accompanied by a rectified linear unit. So a convolutional layer is just whereby your algorithm would do feature extraction. So some filters will be applied on your input image. Usually the input image would be an image of 32 by 32 pixels with 3 channels being the red, blue, and green channel. And usually filters will be applied across the image, and then these filters would learn different features that make up your sources. And then from there, they will be accompanied with a nonlinear activation function, which is called the ReLU in this case. And then another layer is a pooling layer. So a pooling layer is just a layer that downsamples your image. So it does this by taking maybe large values in a given window, or maybe just averaging over them. And then the last layer is it's a fully connected layer. So this layer that's shown here is usually connected with all the weights and your features from the previous layer, and then they are fully connected here. And then from there, this layer would be used maybe to produce the output or your classification or your regression, depending on the task we are using. So yes, we also used something like this. I mean, the reason, maybe if you don't know, they're called deep, it's because you would stack a lot of these layers together to create maybe a network with about 23 layers, for instance. This is what I'll be talking about here. So moving on, like I said, there's been a lot of research regarding the application of deep learning or maybe convolutional neural networks to astronomical data. But however, at the time I started my research, deep learning algorithms were sort of trained to classify only one source per image. For instance, one in the image I'm showing typical radio sources. Please note that this is not how they will be in the sky, or you would see them in the real data. But usually deep learning algorithm will be trained to classify one source per image. So for instance, one would have to generate an image on this source and classify it, an image on this source as well, something like that. So that was a bit of a challenge when coming to real data, because like the image I showed you for Meerkat, these radio sources are relatively close together in the sky. And another challenge was the fact that most of these algorithms were trained on traditional classes, for instance, FR1, FR2, or bent or something like that. So that means when facing a weird morphology, it's never kind of seen before, it would kind of struggle. So those were kind of the two main challenges for deep learning applications at that time to astronomical data. So moving on, and at that time as well, there was a concern in I mean the community, the computer vision community, because usually you would have to train a machine learning algorithm for a specific task and use it only for that specific task. So people are starting to wonder if you can take a machine learning that's trained on one instance and use it on another instance. So that's what we came towards. So we came across this deep learning algorithm called CLAVEN. CLAVEN just stands for classifying radio sources automatically with neural networks. And yes, it was from a paper published in 2019 by Chen Wu. And what was special about this algorithm? I guess it was the two additional layers they added on their two additional networks, I might say, they added on this network. For instance, on this image I'm showing you, it's just the data flow. I mean, you would have your radio image here, and then you go through some pre-processing, and then through the convolutional networks that will learn your features, the feature of the data, and then it would go through the localization network. So in this network, a region of interest are sort of predicted, and different sources on your image are located. And then another network is recognition network. So this network recognizes the different morphologies on the image. So this algorithm was state of the art in 2019, I think, because of these two networks added to it. And so because of challenges of having to take that, because it takes time to build, train, and optimize these algorithms. For instance, this algorithm had about 1.4, roughly 1.4 million trainable parameters. So as you can already, it's a huge task to sort of build, train, and also optimize this sort of algorithm from scratch. So another thing that was, like I said, I mean, people were concerned about having to use a machine learning algorithm for a single task. So people were looking at using this machine learning train for this instance, applying it on a different instance. So people started looking at something called a transfer learning, whereby you would take what was learned from one instance and use it on another instance, whether by retraining or directly classifying. I'm sorry, I just saw the question from the chat. Sorry, I missed it. And someone is asking, is the region of interest task similar to deconvolution? Yes, I would say, but I'm not sure about it, because I mean, like for instance, the network learns these features, and these features are also shared with this network. So in a way, it takes the results from the convolution phase and then first boxes. So I would say I would agree with you. It's similar, but I'm not sure. Sorry, hi Sunil, can you still hear me? I'm not sure, it's a bit quiet.
Yes, you are audible. Yes.
Okay, great. So I hope I answered the question in the chat. If I didn't, we can talk about it more. So going on, yes. So as I was saying, we set out to test transfer learning, that is taking something that was learned on some instance and using it on a different instance. So in this case, we set out to use CLAVEN. I mean, CLAVEN, as you will hear later, it was trained using multi-wavelength data from first survey. First is a radio survey, and then an infrared image data from WISE all-sky survey. So going on, first to understand how Clever works, one has to understand how it was trained. So it was trained using the data from AVZ project. So AVZ stands for Radio Galaxy Zoo. And the Radio Galaxy Zoo project is a citizen science project whereby citizen or people can go in there and help classify these different sources. So for instance, when one goes into the link shared here, you would go through some tutorials to help you classify these sources. And in one of the web page, one of the pages when classifying these sources, this is something you will see, whereby on panel A, I'm showing this. You would be shown a multi-wavelength image whereby radio data from first is overlaid with infrared data in the background from WISE. And then from here, you would have these sliders and buttons, and you would be asked to click on any radio contours. So you would click on the contours, and then you would be asked to click on the infrared host or the associated infrared source. And also more questions will be asked to the user to help classify these sources. And then from there, these classifications were aggregated and a catalog of them were produced. So at that time, this was by far the largest catalog. I think it had over 75,000 classifications at the time for radio sources, if I'm not mistaken. So yes, I mean, Clever was trained using these data for the data from this project. So it followed a similar approach. They used 3 arc-minutes instead of 2 arc-minutes image that was used in that Radio Galaxy Zoo project. But in this instance, they tried to use different inputs. For instance, you have the F, D1, D2, D3, D4 image. So and all of them are fed to Clever in PNG format. So you would have F image that is only a linear. I think it uses a linear scale, and then it's converted to a PNG file. And then here you would, on the D1 image, you'd apply a log scale. And then D2, you would take the red channel of infrared image and overlay it on the on D1 to produce D2, and then D3 would just make this a contour. So you would have the radio data as a contour. And then D4, you would just mask a region containing only the radio signal. So Clever was trained using these different inputs. I mean, as you can see here, others help Clever see the interplay between infrared and radio data. So, and I think that's why Clever was produced better result when it was trained. Oh, by the way, Clever was trained. Sorry, Clever was trained to instead of classifying traditional classes, it was trained to classify classes in terms of components and peaks. And components in this case are referred to discrete or spatially separate radio source components that are detected at the flux density threshold of 4 sigma. And then peaks refer to the number of resolved peaks that can be identified occasionally within the same component. So yes, we have 6 classes, which is 1C, 1P, 1 component, 1P, 1 peak. So that's a compact object or point source. And then we have 1 component, 2 peaks, up to 3 component, 3 peaks. So as you can see, using these 3 different, using these different input images and using performance metric called precision. I'll talk about it later. D4 image seem to perform better for most of these classes, except for 2 component 3 peaks and 3 component 3 peaks. I think one of the reasons is because there was not a lot of instances in the training data for these sources. So probably that's why it underperformed in that instance. And on average, the D4 performs better. So for our case, to test transfer learning, we used our data from GMRT observations. So this is the data. I'm showing you an image from GMRT observation at 610 megahertz of the LSN1 wide field. Yes, so this is the image from Ishwar Chandra et al. So, and as you can see, there's a lot of sources in this image. I think this one is only 1.5 times 0.5 square degrees. I'm not sure about it, but as you can see already, there's a lot of sources and some of which are complicated. So this is the data we used for our, this is the radio data we used for our case. So like I said, yeah, we used GMRT data observed at 610 megahertz of the LSN1 wide field, and it had covered about 13 square degrees with an RMS of about 40 microjansky per beam and a resolution of 6 arcseconds. So in that field, they used PyBDSF to detect this, to produce the positions of the sources, and they cataloged about 6,400 sources above detection threshold of 5 sigma. So here I'm just showing you an example cutout with the two images here on the radio. So it's the 3 arc minute image centered at this source here, even though it's faint, but there's a source here. So we generated 3 arc minute cutout images from each source position from this catalog. So we have about 6,400 images in that case. And then what we then did, we also have got the counterparts from WISE All-Sky. So I'm sure shown by the infrared here. So it's the same region, just in infrared. So the results here, so the blue, I mean, as you can see, the blue boxes from Clarion as well as the predicted class and the probability accompanied. So as you can see, given Clarion these 2 images as input, the radio only and also the infrared fused with radio. So this is the output we get. Clarion was able to detect these 2 radio component or sources in this image, and also it was able to correctly classify them for both images. So yes, this is what we, these are the typical results we have from Clarion, and here are some of the results. So we have 1 component, two peaks in this case with probability score of about 97%. And we also have some sources at the edge, but I think this is, this in a way, we can get rid of it because we generated images on each source position. So there's another image where this source is centered here and it's correctly classified, I think. So here's another example where Clarion detected and classified 2 component 2 peaks, and also detected detected this as a 1 component 1 peak. I guess this was observed in a couple of results because Clarion in a way is also trying to determine whether some components are associated with a certain source or not. So we have some sources that have classifications like this, but it's something we can filter out in the end. And here are some of other examples. So we have 1 component 3 peaks with a probability score of 96, and we also have a typical FR2 example that Clarion was able to detect and classify accurately. So yes, these are some of the examples we have from Clarion. So I'm showing you the D4 or fused results only because Clarion showed better results and when using the D4 image as an input, but I'll talk more about it later. And also, what was nice about Clarion is that, I mean, it was trained using a 3-arc-minute image, but you can extend it to work for an image as large as this is a 15-arc-minute image. As you can see, Clarion was able to detect the 2 radio sources in that image. So here I'm just zooming in those detections there. So we also examined overall Clarion's result in terms of the predicted classes. So this is a histogram displaying overall distribution predicted of the predicted classes for the D1 and the D4 dataset. As you can see, as expected, Clarion predicted that the area is covered by mostly point sources, which is what is expected. But however, we have some concerning 3-component 3 peaks here. So as you can see, for the D1 dataset, it predicted about 20% of these sources, whereas the D4, there's about 2%. And I think this was revealed when the reason for this was revealed when we observed subset of sources that belong to this class. For the D4, I think we saw that Clarion was a bit of confused by unresolved sources that were sufficiently close together. So it regarded them as a single component with 3-component 3 peaks. But as you can see, when using a multi-wavelength image or the D4 image, the results substantially improve. That is, we decrease this spurious spurious detections a lot, and we have something like 2% for the D4 dataset. So that's one of the main indications that D4 dataset was performing better than the D1 dataset, which was consistent with what was presented in the Clarion paper. So going on, I mean, because our data set didn't really have something like a ground truth whereby all the sources in that field were classified and something we can compare with. So we didn't, it was not really straightforward to do some performance evaluation. However, we visually inspected a subset of 1,000 randomly selected fused images or D4 images and evaluated Clarion's performance when it comes to detecting and classifying extended sources, because I mean, there's been a lot of work that shown promising results in terms of point sources. So now we wanted to focus mostly on the classification and detection of extended sources. So for that, we estimate we found 78 true positives, and we found 7 false positives and 22 false negatives. This is equivalent to 92% reliability or precision. So reliability, because that's the terms that are usually used in astronomy, reliability and completeness. So we have 92% reliability and 78% precision from that 1,000 randomly selected D4 images. So of course, those were kind of promising results from this. And going on, so because of this of Clarion's capability of locating different sources on a given image, so we thought of taking that and using it as a source characterization algorithm. And for this, we defined source characterization in 3 steps. That is detection, detection, classification, and identification. So for detection, I mean, we would have bounding boxes predicted already from Clarion, and what we would do, we would try to get the center of mass or the radio center in this case, and we did that by using a 3 sigma clipped fits cutout, because when doing it on a cutout that was not clipped, we found out that our source positions are usually skewed. So cleaning these images were necessary. And then the classification is from Claran. So we're using Claran's classes. And then for identification, we inject, radio sources in this field. And then from there, we get the closest counterpart, infrared counterpart. But yes, this is only limited for sources with infrared counterpart within this box. As you can see here, the black crosses represent source positions from WISE. So as you can see, we don't have a predicted, but you'll see more later about that. So yes, this is what we define source characterization as. And after this, I'll be showing you some results we have. So here, like I said, the crosses represent positions from WISE. And then we have the line crosses, which represents source positions from PyBDSF. And also we have blue cross, which represent the radio center or the source position from this characterization pipeline we implemented. And we also tried to show the estimated hosts using these different positions. As you can see, PyBDSF works in such a way that it detects these sources by islands. So as you can see, it gave two different source positions, so that it found two different islands, PyBDSF. But using something like Claran in this case, which is able to see that these sources is probably one source, you'd get accurate source positions like this one at the center here. So here's another example whereby PyBDSF gave two different source positions for this source, and we have this radio center position from our pipeline, which seems to be accurate than the two positions from PyBDSF. And also there's this example here. So as you can see, for this particular source, there's three different source positions from PyBDSF, and we only have this one from our pipeline that seems to be the true central position. So yeah, this is what we had from this source characterization algorithm, and this is basically what we did for my research. And so I will go to the summary. And so in summary, the next generation of radio sky surveys poses challenges to traditional methods of astronomical data processing. And we really need algorithm to be doing data processing in near real time. And also in this study, we applied transfer learning successfully by taking what was learned previously and applying it to our case that is a bit similar. And by doing visually inspecting the result, we showed that we were able to see that Claran is substantially more accurate when the multi-wavelength or fused data set is used. And I think this is what I just shared with you. And we estimated Claran's performance for our study using 1,000 D4 images and found reliability and completeness of 92% and 78% respectively. We also turned Claran into a fully fledged source characterization pipeline. So large scale surveys such as ESCAPS EMU and VLS will greatly benefit from such work. EMU will be a 1.4 gigahertz survey with 2.5 ARCSec resolution, while VLS will be a 3 gigahertz wide area survey with 2.5 ARCSec resolution. So EMU and VLS will overlap over a large portion of the sky and will thus allow multi-frequency and multi resolution studies of the radio sources. And with that, I mean, if you saw the recent publications from Meerkat observation, you will see how it is important to have frequency and multi-resolution studies, because these sources are often complicated, and with current surveys, we see emission that was not seen previously. But Tlaran is showing great potential of classifying, detecting and classifying complex sources. So I think such surveys will benefit from this work. And for future work, like I just mentioned, we'll be looking to apply this to EMU and VLS, and for that we would use unwise or cat-wise maps that are produced over the full sky. And the reason because unwise or cat-wise provide improved angular resolution and depth. As you can see, I'm showing you a comparison between wise and unwise for the same vision. So as you can see, unwise or unblurred wise has a better angular resolution and depth. So this will be beneficial when having to apply this study to EMU and VLS. And also we'll be looking to apply this over deeper and smaller areas such as Meerkat Mighty survey. And for this, we will use better IRAC images, which have better angular resolution and depth with respect to unwise, as shown in the figure here. In the figure at the top, I'm showing you unwise and compared to Spitzer for the same vision in the sky. As you can see, Spitzer has a better resolution than unwise. So this will be beneficial when having to apply this to the mighty data. So yes, I think that's all I had for you. Thank you for giving me time to talk to you. Are there any questions? I think I will leave it on the slide here.
Yeah, thanks, Chaka. So there are many hands raised. So basically, I will ask Andy to start questions. Andy, please unmute you also.
Okay.
Hi, sorry, that was an applause, not a hand. Thank you very much for the talk.
Okay, thank you.
Okay. So if there is no questions from Andy's side, please, Sriram, you may ask your question.
Hi, thanks for a great talk. So if I understand correctly, your inputs are the imaged continuum image of the area and also the WISE data, which forms the D4, right?
Yes, yes.
Okay, so what was the input for the PyBD BDF versus the other algorithm that you tested? Did it also have an infrared?
Okay, sorry, maybe yes, I was not clear enough. I mean, the PyBDSF only, I was just comparing its position with our pipeline's position. So PyBDSF only what it does, I mean, it takes that full map and then tries to find the source positions of the radio sources in the radio image. Really, that's what it, yes.
So PyBDSF is not a machine learning algorithm?
Yes, PyBDSF is not a machine learning algorithm. I mean, you would have, when using it, I think you would have to tweak a lot of parameters for you to detect all the sources well enough. But yes, bottom line, it's not a machine learning algorithm.
Another question I had was this is performed on a, I mean, this algorithm is trained on a low resolution, low sensitivity model, which is obviously different from Meerkat. So does that in some way affect source detection in a high resolution spectrum?
Yes, I think it does. I mean, talking about this, there was a paper from, if I remember correctly, Tang et al. And Escape and them. So they tried to check how transfer learning would, the effect of having to move from lower resolution to a higher resolution. I think they were using something like FIRST and VSS. So I think their results showed something like the results improve going from higher resolution to lower. I'm not sure about that, but I think, yes, it was affected. So one would have to find a better way to do it, I think. But a similar study has been done for something like this, I think.
Okay, thanks. I have one more question, but I'll wait for others to ask the questions. Thanks.
Okay, thanks.
Okay, thank you, Sriram. I think now we can take questions from Jacinta, if I'm not making it so weird.
Yes, Jacinta, thanks. Thanks, Chaka. That was a really great talk. How does it work on different scales? Like when you're associating different sources, different components with one source, does it prefer kind of for this to happen on small scales? Or for example, I'm thinking about Canada identified giant radio galaxies where the components are separated by several arc minutes.
Yes, I think that's an important question you're raising there. I think we did try a similar thing. I mean, for instance, there were some cases whereby, an FR2 almost filled the whole 3 arc minute image, and sometimes you would have this algorithm only detecting 3 separate components rather than the whole source. But then when moving it to a smaller scale or using a larger image like a 15 arc minute image, whereby this source will appear smaller, it was able to detect it far more better. So I think, yes, scaling played a role as well. And maybe for giant radio galaxies like the one published in your paper, yeah, you would need to go to smaller scales for this to work properly, I think.
Okay, awesome. Thank you.
Okay, great. And now we can take another question from Orabile, please.
Yes, hi Chaka. Interesting talk there. Cool stuff. I just wanted to ask, am I right if I'm saying this is like a source detection and characterization pipeline? And if so, how easy is it to implement and how does it scale?
So maybe I can start about scaling. So scaling part, we haven't really tested it in that regard, but being easy, it's very easy because it's an end-to-end pipeline. If you have maybe your FITS image for radio and infrared already in place, you can easily classify sources and detect them. And for source characterization pipeline, in this case, you would have to have some infrared source positions already in place, or maybe you can use some Python algorithms to get that. But yes, it's an easy algorithm to use, and it works in an end-to-end manner. So you would have little to no. You don't have to be there to watch it all the time, I would say.
Okay, thanks. Cool.
Okay, great. Now we can take questions from Sazrin. Please, Sazrin.
Hi, yes. Hi, Chaka. Thanks for the great talk. So you mentioned it's quite easy. I'm sorry if this is a thing, but you also talked about multi-wavelength or fused data sets. How easy is it to incorporate other wavelengths? So not just Ys and the radio, but maybe X-rays or optical?
I'm not sure about that, because I mean, it was trained to work on the two, so probably it would the algorithm on its own would struggle to work on and maybe go into X-ray and beyond. But maybe that's something it could be trained to do. But on the case of being easy, I think the pipeline, because it uses DS9, so it will be easy to have those images in place. But I think the problem would be actually having the algorithm detect sources in such a way.
So to make it multi-wavelength for other wavelengths, you'd need to add different filters, I guess, and different training data.
Yes.
Yeah. Is that easy to do, or is it quite hard to? I mean, I have no feeling for this. Sorry.
I think because I haven't seen something like that being done properly. I think maybe it will be an easy thing to do, but if one can, like for instance, what they did here, try to find a better input to give to the algorithm, maybe have these different inputs, whereby you're having your X-ray data overlaid in this fashion, and I think maybe that way it would be easy to really learn how to work with such data.
Okay, cool. Thanks.
Thank you, Sharon.
Chaka, in fact, I was also curious to know in the very same question what Sazrin asked. Like, this will be very cool if we can have X-ray also on board, because in upcoming years we will have really. I mean, we already have Erosita, and in upcoming years we have Athena-like missions. So it will be if we can have X-ray included in this kind of approach.
I agree with you. I agree with you. So maybe it's something worth looking at in the future.
Yeah, I mean, biggest challenge will be like, because the parameter range for your training data set will be entirely different. So
yes,
you need
that's true.
to finalize some criteria for selecting X-ray sources, and you may be surprised to have many non-associated sources or even undiscovered problems.
That's true. Yes. So I definitely agree with you there, and probably it's something I will look into in the future when working with this.
Yeah, great. So Sriram, can you please ask your question?
Hi again. So I thinking about barcode integration because we are dealing with large data sets here. Are you familiar of any unsupervised learning models that can deal with all the side lobes and all these things that the raw data will have, something like a clustering, a cocktail party algorithm, or something like that?
I'm not sure, but I think there was a fellow student. I mean, Busiso was working on something like that. I don't know if you know Pink. Do you know Pink? So no. Pink, it's some algorithm that uses coherent maps. So it's self-organizing maps kind of thing. So yes, it's unsupervised, and it was, I think it gave promising results as well when it came to classifying such sources. So maybe that's something you can look into. Other than that, there's no algorithm that I know that can do something like this.
Okay, yeah, thanks.
Thanks.
Yeah, great. So any other question from? No. So basically, we still have some time left for a couple of questions, but anyway, overall, very nice talk and very nice discussions followed. And I will